Let's discuss chemical equilibrium. So up until now, we have majorly seen that in case of chemical reactions, the reactants are getting converted into products. Okay, so reactions are majorly going from reactants to products. They are going from left to right. But now let me tell you that in most of the chemical reactions, it's actually a reversible reaction, meaning that the reactants are getting converted into products, and at the same time, the products are also getting converted back into reactants. What does that mean? Let's take a look. So let's say I have this particular reaction to begin with. In a reaction vessel, we have reactants A and B. When the reaction is beginning, there are no products present, right? Only thing that we have is A and B. And how does a reaction occur? For a reaction to occur, these reactants have to collide with each other with sufficient energy and in a proper orientation so that they can be effectively converted into products. We saw that in chemical kinetics, right? So same is going to happen here in this particular vessel. Reactants A and B are going to react with each other. They're going to collide with each other and they will be converted into products. We saw in chemical kinetics that rate of a reaction depends on the concentration of our reactants. So at this point, these are our reactants. So the rate of this reaction from reactants to products, which is called the forward reaction, is going to be really high. As the time progresses, more and more A and B are going to react to produce C and D. So now my reaction vessel will have C and D as well, right? As the products are being formed, these products are going to collide with each other as well. And as they collide, if they have enough energy and if they are colliding in the correct orientation, they will be converted back into reactants. And this reaction that is going in the backwards direction or the reverse direction is called the reverse reaction. Okay, so what will happen to our forward reaction? Since we are using up more and more of A and B, so the concentration of reactants is going down, which means that the rate of forward reaction is going down as time is progressing. And as time progresses, more and more C and D will be produced. So C and D concentration is going to increase, meaning the rate of reverse reaction is going to eventually increase with time. And after a certain time of period, the rate of the forward reaction is going to become equal to rate of the reverse reaction. And this time point is called the equilibrium. This state is called chemical equilibrium. Now at this state, the reaction essentially becomes stable. The concentrations of the reactants and concentrations of products are constant now, meaning that the concentrations are not going to change. Now, there's a major difference when I say that the concentrations have become constant. Okay, it does not mean that the concentrations have become equal to each other. It does not mean that now A is equal to B or concentration of A and B is equal to C and D. Okay, that does not mean that concentrations have become equal. Only thing that happens at equilibrium is that concentrations have become constant. So concentration of A is not going to change. Concentration of B is not going to change. It's different from each other, but they are just constant. Okay, this is called the state of equilibrium. It does not mean that the reaction has stopped. So this equilibrium is not a static equilibrium. This is a dynamic equilibrium, meaning that the reaction is still happening. Reactants are reacting to form products. At the same time, products are reacting with each other to go back to reactants. Okay, so if we look from outside, our vessel is going to look same. Okay, the amount of A, amount of B, amount of C, and amount of D will look same from outside, but the reaction is still happening. Okay, so the rate at which A is being produced, at the same rate it is being used up. All right, that is why we say that rate of forward reaction has become equal to rate of reverse reaction, and that is the state of chemical equilibrium. So how do you define that? It is a dynamic state where the rate of forward reaction becomes equal to rate of reverse reaction, and the concentration of products and reactants are no longer changing, and that means that it has become constant. That does not mean that they have become equal to each other, right? That is the most important thing, because that's one mistake that a lot of students make, assuming that since the reaction is stopped now, it's the concentrations have become equal. That is not true. The concentrations have become constant and the reaction has not stopped. It is still happening. Only thing is that now there is no change in concentration. So from outside, it seems like there's no more reaction happening, but the reaction is still continuing. Okay. All right, so let's take an example of a chemical equilibrium with a chemical reaction. For instance, this reaction N2O4, gas is changing to 2NO2. So our reactant is N2O4, products are NO2. So in this case, in the beginning of the reaction, we only have reactant, which is N2O4. Therefore, you see the concentration is really high. For NO2, the concentration is really low, or essentially zero in the beginning, right? As time is passing by, the concentration of N2O4 is decreasing and concentration of NO2 is increasing because it is products, more and more of it is being produced. At some point after certain amount of time, the concentration of the reactant N2O4 becomes constant, and same thing happens with the concentration of our products, which is NO2. And this state right here is called the state of equilibrium. So after this, the concentration of N2O4 is going to stay same and concentration of NO2 is going to stay same. So you can see right here, they're not equal to each other. Only thing that has happened is they're not changing anymore. So this is called the state of chemical equilibrium, right? Now let's try to understand how can you actually write an expression for equilibrium constant. So based on kinetics, we can, if I tell you this is an elementary reaction, meaning this is the mechanism and this is the elementary reaction, no other steps are involved in this particular reaction, can we predict what would be the rate of forward reaction? If it's an elementary reaction, yes, the answer would be yes, we can predict the rate of forward reaction. So let's write down what would be the rate of forward reaction. Rate would be equal to rate constant for the forward reaction times concentration of our reactant raised to the power 1. 1 comes from stoichiometric coefficient, which is only true if this reaction is elementary reaction. Can we write down, similarly, can we write down what is the rate of reverse reaction? So rate of reverse reaction in this case would be equal to rate constant for the reverse reaction times the concentration of our reactant, which now, since it's a reverse reaction, our reactant is NO2 raised to the power 2, stoichiometric coefficient again because this is an elementary reaction. Now we know what happens at equilibrium. At equilibrium, rate of forward reaction equals rate of reverse reaction. So essentially we can rewrite this expression as, we just plug in these values right here and that would give us this expression. Now if I divide both the sides by K reverse and the concentration of N2O4, that would give me this right here, right? So rate constant of forward reaction divided by rate constant of reverse reaction can be written in this form. Now we know that rate constant is always constant, right? As long as the temperature stays same. So at a given temperature, the rate constant stays same. It does not change, right? So rate constant for forward reaction is a constant term. Rate constant for a reverse reaction is a constant term. So at a given temperature, both of these are constant, meaning their ratios are going to be constant, right? So this constant can be written out as equilibrium constant, or is defined as equilibrium constant. So how can you write the expression of equilibrium constant? Equilibrium constant equals concentration for this particular reaction right here, concentration of products raised to the power 2, where did this 2 come from? Stoichiometric coefficient, over concentration of reactant, which is N2O4 raised to the power 1, which is again the stoichiometric coefficient. And since this expression is written out in terms of concentration, we usually write down the equilibrium constant as capital Kc. Now, next important thing here is that rate constants are always written as smaller case k, and equilibrium constant is always written as uppercase K. Okay, so whenever you see capital K or K in caps, that is talking about equilibrium constant. And whenever it's in small, that means we are talking about rate constant. So that's the major difference. That's where you should never get confused, right? So if you're talking about a general reaction, for instance, like this, where AA plus BB changes to CC plus DD, where all caps are essentially reactants and product, and everything in small or lowercase is essentially the stoichiometric coefficient. We can write down the equilibrium constant as products raised to the power their stoichiometric coefficient over the concentration of reactants raised to the power of their stoichiometric coefficients, right? So in this case, we have two products, so it's concentration of C to the power of C times, this is not plus, remember it's times concentration of D to the power of D divided by concentration of A to the power A and concentration of B to the power B, right? So product concentration multiplied over reactant concentration multiplied to each other. Okay, so this is called the expression for equilibrium constant. Now, even though you see that here in this expression, everything is written out in terms of molarity, since this is concentration, right? Um, Equilibrium constant is still regarded as a dimensionless number. Okay, so this has no units, even though you would assume there would be some units written out based off of this expression, it will be unitless term. Okay, so it has no dimensions. Now, next important thing is that this equilibrium constant is specific at a given temperature. So it's a constant term unless temperature is changed. So at a given temperature, value of K will stay constant for a given reaction. And once the temperature changes, the value of K will also change. Okay. Next thing, very important to remember is that in case of this equilibrium expression, only states of the reactants and products that you're going to include would be gases and aqueous. Okay, so if there is anything that is solid in this given reaction or liquid in this particular reaction, that will not be included in this particular expression. That would be omitted from the expression of equilibrium constant. Why? Because when you're talking about solids or pure solids or pure liquids, their concentrations does not change, right? We are not talking about that is not expressed in terms of concentrations. So only gases and aqueous states are going to appear in this expression. Okay, why is it important though for us to figure out what is the equilibrium? We just figured out what is the rate constant, right? Now we have to also figure out what is the equilibrium constant. Why is that? So equilibrium constant is important because it tells us what is the extent of a reaction. Okay, it will tell us how far a reaction will go before it reaches equilibrium. Okay, what does that mean? So let's say if we have, this is a general expression of a reaction, equilibrium constant, right? Equilibrium constant equals products to the power of stoichiometric coefficient divided by reactants to the power of its stoichiometric coefficient. Okay, so now let's say if for a given reaction I tell you that the equilibrium constant is greater than 1. If it's greater than 1, that means that for this particular reaction I have more products, right? My numerator is going to be higher. That means that I will have more products in this particular reaction when the reaction reaches equilibrium. Okay, so this means that at equilibrium, the reaction will have more products and less of the reactant. So I can say that equilibrium will lie towards the right, meaning it will lie towards the product, and that it is good. This reaction, equilibrium is going to favor products, right? So whenever you see a reaction with K greater than 1, it means that this reaction at equilibrium is going to favor more products. Now let's pick another scenario where K is actually less than 1. If K is less than 1, that means that now the value of K is less, so I have more reactants in my system, correct? Meaning that in this case, at equilibrium, we will have more reactants in comparison to product. So for this particular reaction, equilibrium will lie towards the left, meaning there will be more reactants at equilibrium, and it's going to favor reactants, right? So to sum it up, we can say that a large value of K indicates that the reaction reaches equilibrium, with very little reactant remaining. The reaction favors the product. But if a small value of K, that would indicate that the reaction yields little product before it reaches equilibrium. So reaction favors reactants. Okay. Let's try out a couple examples now. So if for this particular given reaction, can we write down what would be the equilibrium expression? Simple question. Just tell me what would be the expression for the chemical equilibrium for this particular reaction. So for this reaction, it's again based on just stoichiometric coefficient K C equals products over reactants, right? So only thing that we have to remember is that only states that are in gas and aqueous will be included. Anything that's in solid or liquid will be omitted. So for instance, we have in this case, what are our products? There are two products, but in case of our expression, we are only going to include water because that's the only one that's in gas. Iron we are going to omit because it's solid. So K is going to be product, which is water, raised to the power 3. Why? Because stoichiometric coefficient, over our reactant, which is hydrogen gas, raised to the power 3. And we are going to omit Fe2O3. Why? Because it's in solid. Okay. Moving on, here's another example. Can we write the expression for equilibrium constant for this particular reaction? In this case, again, we know it's products over reactant. Now both of the products are in aqueous state, so they will be included. And in case of reactants, there's one which is liquid, so we'll omit that. And this is aqueous, so this will be included. So simple expression would be equilibrium constant equals CH3COO minus raised to the power 1 times H3O plus raised to the power 1 divided by reactants, which is CH3COOH to the power 1, and water, we are going to just ignore it. Right? So that's the simplest kind of question that you can get in case of chemical equilibrium, to just predict what is the expression for chemical equilibrium constant. Okay. Now, next very important term that will come up a lot in case of chemical equilibrium is called the reaction quotient. It is also referred to as mass action expression, or it's abbreviated as capital Q. Now, what is that? For a given reaction, again, AA plus BB changing to CC plus DD, the reaction quotient is written as concentration of C to the power of C, concentration of D to the power of D divided by concentration of A to the power of A times concentration of B to the power of B. This looks very similar to what we just did, right? Very similar to chemical equilibrium. Exactly same expression, right? It's products over reactants, everything raised to the power of their own stoichiometric coefficient. What is the difference though? The major difference here is that in case of reaction quotient, it's the ratio of the concentrations of products and the reactants at any point in a reaction, meaning at any given time point during a reaction. Let's say I'm talking about the initial conditions where time is 0, then this expression would include concentration at that time point. If I'm talking about at certain time point between a given reaction, then this expression would include concentrations at that time point. Okay. Whereas in case of chemical equilibrium, we are majorly talking about the ratio of concentration of products and the reactants at equilibrium. Okay, so that is a major difference. Q is essentially concentration of products and reactants at any given time point, but for equilibrium constant, it's the same expression, but only difference is that you would be using concentrations at equilibrium. All right, now why is understanding Q important for us? Q will tell us, the value of Q is going to tell us how close a reaction is to equilibrium. Okay, we can tell based on Q, is the reaction going to move forward or is it going to go reverse? What does that mean? Essentially, we see that the expression of Q and K is same, right? And so we can say that at equilibrium, the values of Q are going to be equal to values of K, correct? So right here, at equilibrium, we can say that value of Q is going to be equal to value of K. And what is the ultimate fate of a chemical reaction? All reactions are essentially just moving towards equilibrium. So each reaction will keep on going until it reaches the state of equilibrium. That's essentially the fate of each reaction. Okay, until it reaches equilibrium, the reaction is the reaction will keep on happening. Once it reaches equilibrium, it's going to become constant. The reaction is still happening, but everything becomes constant now, right? So if in a given scenario, Q is less than K, that means again the aim of the reaction is for Q to become equal to K. So if Q is less than K, what will the reaction do? The reaction will move towards a situation where K is equal to Q, meaning the reactants are going to get converted into products. So in this case, system will proceed from left to right, or we can also say that system is going to proceed from reactants to product. So more and more reactants are going to be converted into product until Q becomes equal to K. Now, if it's a reverse situation, meaning Q is greater than K. So we know for a given reaction at a certain time point, Q is greater than K. Now, can we predict which direction will the reaction go? Since Q is greater than K, the final aim is for Q to come back down to such that it's equal to K, right? So to come back down, the system is going to proceed from right to left. So majorly, products are going to be converted into reactants now, right? So this essentially lets us predict which direction a reaction will go. Will it go from reactants to products, or will it go from products to reactants? So if a question is just asking you which direction will a reaction go, how can you tell? You can tell it by looking at the values of Q and comparing it to the value of K. Now K is always constant. Remember that for a given reaction at a given temperature, K is constant. Only thing that changes with time is Q. Okay, so we just calculate what's Q, we calculate what's K, and we compare the values. Okay, if it's small, it goes towards the products. If it's greater than K, it goes towards the reactants. Easy? All right. So let's try a couple examples now. For instance, let's try this one on the left. Which of the following is the correct mass action expression for the reaction? What is mass action expression? It's same as reaction quotient, which is Q. So a given reaction, PCl3 gas plus chlorine gas is converted to PCl5 gas. Okay, everything's in gas, so everything will be included first time. What will be Q? Q will be products, PCl5 raised to the power of 1 divided by reactants, which is PCl3, concentration of PCl3 to the power of 1 times the concentration of Cl2 raised to the power 1. Do we see anything like that? Yes, we do. So answer will be B, right? This is completely wrong. These are not the question, the exponents that you see right here. We don't use those exponents. What are the exponents? Exponents are stoichiometric coefficients. Okay, remember that. All right, moving towards the example on right. Which of the following is the correct mass action expression for the given reaction? Copper 2 plus aqueous plus 4NH3 aqueous is getting converted, again a reversible sign, getting converted to, this is a transition metal complex. So it's a complex. We'll talk about those in another video. But important thing here is this is one product and it's aqueous. Okay, so everything will be included. What would be Q? Q would be again product raised to the power of 1 divided by concentration of reactant, which is copper 2 plus to the power of 1, concentration of ammonia to the power 4, right? Do we see an expression like that? Yes. Answer is A. So there we go. Okay. Let's try next question then. So at the start of a reaction, there are 0.249 moles of nitrogen, these many moles of hydrogen gas, and these many moles of ammonia in a 3.50 liter reaction vessel at 375 degrees Celsius. If the equilibrium constant for the reaction, this is a reaction, is 1.2 at this temperature, decide whether the system is at equilibrium If it is not, predict which way the net reaction will go. Okay, so what's given to us is the amount of nitrogen, hydrogen, and ammonia. So amount of all the reactants and products in moles. We know the volume of our reaction vessel. We know the temperature. And what's given to us is the equilibrium constant. So the question is, first, is the system at equilibrium? Second, if not, what is the direction? How do we know if the system is at equilibrium or not? We will have to compare Q and Kc, right? In order to compare them, we have to first figure out what is the value of Q and what is the value of Kc. If we can compare those, if they are equal to each other, we know the system is at equilibrium. If they are not equal to each other, we can then predict what would be the direction in which the reaction goes, right? So let's figure out what is Q for this reaction, and K is already given to us. Okay, so let's first figure out what are the concentrations of our species that are given to us. So what's given to us is nitrogen. The concentration is essentially just going to be moles over liter, right? Moles per liter is molarity. So we take the moles given to us divided by 3.50 liters. This is the concentration of nitrogen initially. Similarly, we'll calculate concentration of hydrogen gas and concentration of ammonia, moles per liter. So these are the respective concentrations. Now, how can we figure out what is the Q? For Q, we go back to our reaction. Q for this reaction, what is the expression going to be? It's going to be products, which in our case is ammonia raised to the power 2 based on the stoichiometric coefficient divided by reactants, which is nitrogen to the power of 1 times hydrogen to the power of 3. So now we just take whatever values we calculated and plug into this expression right here. Okay. So once we plug in those values, we get a Q of 0.61. And what was the Kc given to us? The question told us Kc is 1.2 and Q that we calculated is 0.611. So now, is the system at equilibrium? No. The first answer is no. The system is not at equilibrium. Why? Because the value of Q is not equal to value of K. Okay. Next, the question asks which direction will this reaction? So for the direction, we'll compare values of Q and C. Q is less than C. So we know for this particular reaction, Q is less than K. Right? So since Q is less than K, we know that the reaction will proceed from left to right. It will go from reactants to products. So your answer can be any of these. It can be that the reaction will go from left to right, or reaction will go from reactants to products. Why? Because the ultimate aim is again for Q to become equal to K. Since they are not equal right now, in order to make them equal, Q will have to increase its value. So it's going to go from reactants to products. It will make from more and more products so that this value can increase. Right? Now, we just saw for the action, this is just giving you, it's a repeating a little bit. So when we are talking about a heterogeneous reaction, heterogeneous equilibrium, what does that mean? In case of a heterogeneous equilibrium reaction, it involves the reactants and products in different phases. Like we saw, we have solids right here and gas. It can be include solid, liquid, gases. So when there are different phases involved, we are talking about a heterogeneous reaction. So the equilibrium is for a heterogeneous reaction. We already saw that a pure solid or a liquid always has the same concentration technically. Therefore, the same number of moles per liter of solid or same number of moles per liter for the liquid. Therefore, whenever we talk about expression for Q and K, we only include the species whose concentration change as the reaction approaches equilibrium. So we only include the expressions that are in either gas or aqueous. So for this particular reaction, what will be our expression? Q is going to be equal to concentration of CO2, which is product, divided by reactant, but there's no other reactant which is in gas or aqueous. So that's why we can omit the solids, right? Now, if it's a homogeneous equilibrium though, For instance, like this, we just saw for N2O4 changing to 2NO2. Both are gases, so Kc is equal to NO2 squared divided by N2O4 to the power 1, right? But sometimes when we are talking about gases, we have seen that previously that in terms of concentration can be written in terms of molarity, but for gases it can also be written out in terms of atmosphere, right, or pressure, pascals, kilopascals, atmosphere, whatever may be the unit, but it can also be expressed in terms of pressure of a gas. So if we are talking about, instead of using concentration, if we write out this expression in terms of pressure of gas, in that case, this equilibrium constant, instead of writing it out as Kc, is written as Kp. So whenever we say Kp, that just means that instead of using concentration, we are using pressure now. But everything else still stays the same. So for instance, Kp in this case is going to be equal to pressure of NO2 squared divided by pressure of N2O4 to the power of 1. Okay, everything else, all the rules still apply, everything stays the same. Only thing that changes is that now instead of concentration we are using pressure. So instead of calling it as the equilibrium constant Kc, we call it as the equilibrium constant Kp. This does not mean that the values of Kc and Kp are same. Okay, most of the cases, in fact, Kc is not going to be equal to Kp. Okay, is there a relationship that relates Kc and Kp though? Yes. For a given reaction, Kp equals Kc times RT to the power of delta N. So RT is in parentheses, or value of R times T is raised to the power of N. R is a constant term. Temperature is again a constant temperature, right? At a given temperature we are talking about. So both of these are constant. What's changing here is the delta N. What is delta N? Delta N is essentially the difference in the number of moles of product minus the number of moles of reactants. Okay. So for this particular given reaction, what is delta N going to be? Delta N would be C plus D, which is total number of moles of product minus total number of moles of reactants, which would be minus A plus B. Okay. So that's how you can relate values of Kp and Kc for a particular reaction at a given temperature. Right. Let's try one example right here. So consider this reaction. A plus 2B is changing to 4C. If Kc for the reaction is 0.99 at 25 degrees Celsius, what would be Kp? Okay, so what's given to us is Kc is given to us, temperature is given to us, question is asking us what is value of Kp. Do we know a relationship that relates Kp and Kc? Yes, we know that Kp equals Kc RT to the power N. So Kc, let me write that down right here. Kp equals Kc times RT to the power of delta N. Kp is what the question is asking us to calculate. Kc is given to us. R is a constant value. We know it already. Temperature is given to us as well. So we know temperature. Only important thing is we have to make sure that we are using the right units of temperature. Okay. Delta N, not given to us, but can we solve for delta N? Yes, we can solve for delta N. Delta N is, for this particular reaction, it will be products, moles of products, which would be 4, minus moles of reactant, which would be 2 plus 1, right? 1 mole of A plus 2 moles of the. So this is going to be 4 minus 3 equals 1. So we know that delta N is 1. Now we just plug in all our values into this equation, right? Delta N is 1, Kp equals Kc times R times T to the power of delta N, which is 1, gives us a value of Kp. Okay, moving on, let's try next example. Consider the reaction 2NO2 gas changes to N2O4. You'll see this example multiple times in this particular chapter. So if Kp is 0.480 for a given reaction at 25 degrees Celsius, what is the value of Kc at same temperature? Again, We are being asked to relate Kp and Kc. Do we know a relationship? Yes. Temperature given to us, R known to us, Kp given to us. Now this time the question is asking what is Kc. So first thing we'll do is let's figure out what is delta N. Delta N in this case for the second reaction is going to be product, which is 1 minus moles of reactants, which is 2. So delta N is actually going to be -1, right? So now we just plug in all the values right here. Delta N is -1. So if we want to calculate Kc, we can rearrange this equation or divide both the sides by RT to the power N, and that would give us this expression. So we just plug in the values now. Kc equals Kp 0.480 divided by R times temperature. Again, this is in Kelvin, all raised to the power of -1. That would give us our Kc. All right. Now, next very important thing we are going to talk about. There are a couple rules that we'll talk about. So eventually you will essentially be kind of memorizing these rules, but let me just show you how you actually derive those rules, okay? So it will all make sense. There's not like a lot of memorization. So let's look at rule number 1. So if we take this example, we have a particular reaction A plus B changing to C plus D, okay? A reversible reaction. The equilibrium constant for this reaction is Kc prime, okay? There's a second reaction where we have C plus D is changing into E plus F. Okay, again, it's a reversible reaction. The equilibrium constant for this reaction is Kc2 prime, right? Now we have to see here that C and D are reactant products for the first reaction and C and D are the reactants for the second reaction, okay? Now, can we write based off of this, can we write down what is the expression of Kc prime? Yes, let's write down the expression for Kc prime for the first reaction. It's going to be product. Again, concentration of C to the power 1, concentration of D to the power 1, divided by concentration of A to the power 1 times concentration of B to the power 1. Easy? All right. Now, can we write down the expression for Kc2 prime? Okay. So Kc2 prime is going to be same thing, product E concentration of E to the power 1 times concentration of F to the power 1 divided by concentration of C to the power 1, concentration of D to the power 1. Okay, again, products over reactants, right? Now, what happens if we add these two reactions? Okay, let's add these two reactions. We have seen that in a video before. How do you add chemical equations? You essentially see if there is anything that's common on the reactant and product side that gets cancelled, right? And if there's anything on the same side, a reactant, and in the second reaction we have the same reactant, you add those up, right? So simply we are going to just add these two reactions. We see that C here is a product, whereas C on the second reaction is a reactant. So C produced is being used up, meaning C and C will get cancelled, right? And D will also get cancelled because it's a product here and it's a reactant right here. So it's being produced in the first reaction, used in the second reaction. So what's the overall reaction now? Overall reaction is A plus B is changing to E plus F, right? So let's assume that equilibrium constant for this reaction is Kc, right? So what would be the expression for equilibrium constant for this reaction? It's going to be products E times F divided by A times B. All right, perfect. Now let's just take the first reaction and the second reaction, and I'm going to multiply these expressions of equilibrium constant. So if I multiply Kc prime times Kc2 prime, what do I get? I multiply these two, right? Concentration of C gets cancelled, concentration of D gets cancelled. What am I left with? I'm left with concentration of E, F divided by concentration of A, B, right? That's exactly similar to what we got for Kc, right? So can I say that Kc equals Kc prime times Kc2 prime? Yes, so that is our rule number 1, which states that whenever in a given reaction, if a reaction, for instance right here, if a given reaction can be expressed as sum of two or more reactions, the equilibrium constant for the overall reaction is given by product of the equilibrium constant of the individual reaction. So a given reaction right here, the third reaction, is sum of the first two reactions. Therefore, the equilibrium constant for this overall reaction, which is Kc, will be equal to product of the equilibrium constant for individual reactions. All right. So Kc equals Kc prime times Kc prime 2 prime. Why? Because we just derived it, right? It makes sense. So that's rule number one, that will always hold true as long as the temperature is constant. So if we add two reactions to get to an overall reaction, what happens to Kc? Their Kc's will be multiplied with each other, right? Okay, let's look at rule number two. Okay, so for this, let's take an example of this particular reaction. N2O4 is changing to 2NO2. What would be the equilibrium constant expression for this? K is equal to product squared divided by reactant to the power 1, right? Now, if I reverse this reaction right here, to completely different reaction, okay? It's just reverse of that reaction. 2NO2 changing to N2O4. Now this is my second reaction. What would be the equilibrium expression for this? It's going to be product. Now my product is N2O4, so concentration of N2O4 divided by NO2 squared. If we compare these two reactions are reverse of each other. If we compare their equilibrium constants, we can see that they are also reverse or reciprocal of each other, right? So can we relate them as this? So what this essentially is telling us, that when the equation for a reversible reaction is written in the opposite direction, the equilibrium constant becomes reciprocal of the original equilibrium constant. So if I give you the equilibrium constant for this reaction and I tell you that for N2O4 changing to 2NO2, equilibrium constant is 5, that means that for the reverse reaction, equilibrium constant is going to be 1/5, right? Okay, let's look at rule number 3. So in case of rule number 3, we are talking about a reaction A plus B is changing to C plus D. Okay, forget about this rule. It should have come up later on. So if we are just looking at rule A, reaction A plus B changing to C plus D, let's write down its equilibrium expression. Kc is concentration of product, C times D over concentration of reactants, A times B. Right? Now, completely different reaction, okay, which is 3A plus 3B changing to 3C plus 3B. So what would be the equilibrium expression for this reaction now? For this given reaction, equilibrium constant expression would be C raised to the power of 3, right? Concentration of C to the power of 3 times concentration of D to the power of 3 divided by concentration of A to the power of 3 and concentration of B to the power of 3. So that would be the equilibrium constant expression for this reaction. Now, what is the difference between these two reactions? The only difference I see is that this reaction has every reactant and product has been multiplied by a stoichiometric coefficient of 3, right? Everything is just 3 times of the top reaction, right? So can I relate these two expressions as well? That means that Kc for this bottom reaction is essentially Kc for the top reaction cubed, right? If we relate this, this is essentially just cube of the top reaction. So what that tells us, that whenever coefficients in the equation are multiplied by a factor, equilibrium constant is raised to a power equal to that factor. So essentially, if there is a reaction of A is to B, A is changing, sorry, it's a reversible reaction. So A is changing to B and the equilibrium constant for this reaction, let's say, is 2. Now I ask you, if the reaction is 3A changing to 3B, can you tell me what would be the equilibrium constant for this reaction? Yes, it's the same reaction except that now this reaction is essentially 3 times of the top reaction. So stoichiometric coefficient is essentially 3 times. So if I'm multiplying this reaction by 3, what happens to Kc? Kc is raised to the power 3. So Kc for this reaction is going to be 2 cubed. Okay, so that's the last rule. Okay, so in summary, what's happening? If I add the two reactions, let's say if I'm adding uh, reaction, what happens to values of K? K gets multiplied. So K1 times K2. Okay, so Kc will be now K1 times K2 if I'm adding the reaction. This is rule number one. Rule number two, if I reverse the reaction, Kc will be reciprocal of the previous reaction, equilibrium constant. Third rule is if I multiply the reaction by a stoichiometric coefficient, let's say n. If I multiply the reaction by n, Kc now will be whatever was the K1, let me say K1 for this particular reaction, right? Whatever was the K1 for the given reaction, all raised to the power of n. Right, so that helps you to essentially compare the reactions and figure out what would be their equilibrium constants. Let's take a couple examples in this case then. So for instance, we have this reaction. What's given to us is for N2 plus 3H2 changes to 2NH3. Kc is given to us as 500 at a given temperature. For part 1, what would be the Kc for following reaction? Let's just focus on part 1. So for part 1, is there a relationship that we see between what's given to us in question and what's being asked? Yes, we see that the reaction that we want to calculate Kc for is essentially just reverse of the top reaction, right? So if this reaction is just reverse of that, what happens to Kc? If it's reverse, remember the rule was if the reaction is reverse, Kc becomes reciprocal, right? So the top reaction Kc is 500. The reaction which is reverse would be the new Kc for the bottom reaction is going to be 1 over 500. Right? Now let's do part number 2. Second question says, can you figure out what is the Kc for this reaction? Now let's compare our first reaction with this reaction. What is the relationship that we see? We see that in order to get the bottom reaction, what have we done? We have just N2 plus 3 by 2 hydrogen is changing to ammonia. Right? So what is the difference between this reaction and what's given to us? We just multiplied this reaction by half, right? Everything has been multiplied by half. So instead of 1, it's 1/2. Instead of 3, it's 3/2. Instead of 2, ammonia, it's 1, meaning half of that, right? So if we multiply this reaction by half, we'll get this reaction. So if we are multiplying anything, if we multiply reaction, what's the rule? What happens to Kc? Kc essentially is raised to that particular multiplication factor. So in this case, what is our n? In this reaction, n is essentially 1/2, 1 over 2, meaning what would happen to our Kc for this reaction would be previous reaction Kc raised to the power of n. So 500 to the power half, meaning square root of 500, which is essentially this. So that's how you can predict what would be the value for the Kc for any reaction if it's related to the previous reaction, and we know what is the value for equilibrium constant for that particular reaction. Okay. Now let's move on to one more example. So consider this reaction. NO2, 2NO2 gas changes to N2O4 if Kp is 0.480 at 25 degrees Celsius. Does the reaction favor product or reactant formation? Okay, so at a given, for a particular reaction, Kp value is given to us. Kp, let me write down here, Kp is 0.480 at 25 degrees Celsius. Okay, so for this particular reaction, Kp is given to us. Question is, Does the reaction favor product or does the reaction favor reactant? We know that Kp and Kc, same rules apply, everything is same. So if Kp is less than 1, we know that in this case, we can see that Kp is less than 1. So we know that whenever the value of Kp is going to be less than 1, meaning the reaction is going to favor reactants, right? So if the value of equilibrium constant is less than 1, it is favoring reactants, right? So this is just kind of summary of everything that we just did. So how do you write the expression of Q for a given reaction? How do you write the expression for K for that particular reaction? So for instance, in this case, A to B, K is given by K reference. If we reverse this reaction from B to A, K would be reverse of the previous K value, okay? Now this is two-step reaction, A is changing to C is changing to B. So if we know K for overall reaction is going to be multiplication of K for the first and K for the second. If the coefficients are multiplied by n, K becomes to the power of n, right? Reaction with pure solid or pure liquid components such as A solid, if that is the case, then we will not be including that solid in the expression. Only component that would be included in the expression, they are talking about A to B here, only component that would be included is essentially just that other component which is not solid or liquid, right? So just summary of everything that we just did. All right, now let's try this example. This is where it gets a little bit tricky. So a chemist wants to find Kc for the following reaction at 700 Kelvin. So the reaction we want to figure out Kc for is 2 ammonia. Let me just put this line right. So 2 ammonia gas plus 3 iodine. Oh, gas is changing to reversible reaction 6Hi gas plus nitrogen gas. The question is to figure out Kc for this, right? Use the following data. So what's given to us is nitrogen plus hydrogen changes to ammonia, Kc is given, and hydrogen plus iodine changing to 2Hi, Kc is given. So using these two reactions, can we figure out what is the Kc for this reaction? Okay. So first important thing is, if we just use this, let me just write it down better. So rewrite this. So 3 gas, this is plus 3 I2. Okay, so if this is a reaction, we have to predict this out. Two reactions are given to us. So do we see a relationship between this? If we just add the two reactions, do we get this? Doesn't look like it, right? So it's not that straightforward that we can just reverse or add or do something, multiply it by a coefficient and get to our reaction in question. That's not true in this case. So we just have to use our logic now. How can we add these two reactions, or what can we do to these two reactions to eventually get to this? So in order to do that, the first step that I would advise is I start with one reactant at a time. I do not worry about products. I just start with reactants. Okay. So the first reactant in our case is ammonia. Let's see which of these two reactions has ammonia given to us. It's the first reaction, right? What I want is ammonia to be my reactant. What's given to me is ammonia as a product, right? Which means I'll have to reverse this reaction. So the first step that we'll have to do is that we'll have to reverse the first reaction. So if I reverse the reaction, I do 2NH3 gas changes to nitrogen gas plus 3 hydrogen gas. So first thing that I know now, since I'm reversing this reaction, what would happen to my Kc? My Kc for this reaction is going to be, since I reversed it, it's going to be reciprocal of Kc1, correct? So I can figure that out now. Kc for this reaction is going to be 1 over Kc1. So I'm going to write this as Kc prime. Okay. So I get my first reaction. I don't have to do anything. I need 2 ammonia. I get 2 ammonia from right here. Okay. I don't have to multiply it with anything. Now let's look at the second reactant that we have right here in the overall reaction. Always look at what you're trying to get, okay? Just focus on this. The first reactant done. Now let's look at our second reactant. Second reactant, I need iodine, I2. Where is my iodine in the given reactions? I see iodine in my second reaction. Perfect. So it's in the reactant. I want it on the reactant side, so I don't have to reverse it. So I can just write it as H2 gas plus I2 gas changes to 2HI gas. But I want in my reactant, I want it as 3I2, right? What I'm getting from here is only 1 iodine gas, 1 mole. So what would I have to do? I'll have to multiply this reaction by 3, right? So if I multiply this reaction by 3, what does that give me? So let me rewrite this in that case. So if I multiply this reaction by 3, that would make hydrogen as 3 H2 times, plus 3I2 gives me, instead of 2, it's going to be multiplied by 3. So that gives me 6HI, right? Now that I multiplied this reaction by 3, what would happen to my Kc? So write it as Kc2 prime for this reaction is going to be whatever was my Kc previously to the power of 3, since I multiplied this reaction by 3. Okay. Is there any other reactant that I see? No. So that's all, I think, right? Now, first thing, it's a hit and trial approach, okay? So we're just going to assume that this is done. So let's try and add these two reactions now, okay? So 2 ammonia, do I see any ammonia anywhere else? No, so that will come right here, 2NH3 gas. It's one of my reactants. Let's look at the other reactant now. I have 3 hydrogen right here. First, just do the reactants, then we'll move on to products. I see 3 hydrogen moles. Are there any hydrogen involved anywhere else? Yes, I see 3 hydrogen in products as well. So what will happen to my hydrogen? It's being used up, it's being produced, so they cancel out. So perfect. Now I move to the next reactant, which is iodine plus, do I see iodine anywhere else? No. So that would be 3I2 gas. All my reactants done? All right, so there goes my arrow. Now I come to products. Do I see any nitrogen anywhere else? No. So that would be one of my products. What hydrogen is already gone. Next I see is HI. Do I see it anywhere else? No. So that means that would be my next product. Okay, so if I add these two reactions, I get this. Is the same reaction that I'm looking for? 2 ammonia, 3 iodine, 1 nitrogen, and 6HI. Perfect. So that is exactly what I'm looking for. So what did I do right here? In order to obtain this reaction, oh, too much zoomed out. In order to obtain this reaction, okay. So to get to this reaction, what I did is I added these two reactions. So if I added these two, what happens to my Kc whenever we add? Okay, let me rewrite this. So whenever we add two reactions, what happens to Kc? Kc gets multiplied. Whenever you add two reactions to get to overall reaction, Kc for overall reaction is multiplication of the previous two Kc values. So it's going to be Kc prime times Kc2 prime. Okay, meaning my Kc overall reaction is going to be 1 over Kc1, 1 over Kc1 times Kc2 cubed. So that is going to be 1 over 0, 1 over 0.343 times 54 cubed, right? So let's see if that's the same thing. Yes, so what we did is we did 4 over 0.343 first, and we figured out 54 cubed first, and then we multiply those two values, and we got our final Kc for overall reaction.